Let's take a look at two solenoids. They are merely pieces of wire that I have chosen to wrap around a cylindrical object. On the left and the right, the current is going in the same direction. Now the way I indicated my shading is for you to imagine that the current comes toward me, and then if I have a gap here, it means it's going behind me, and then comes towards me again, and then behind me. So using the right hand grasping rule of Biot-Savart, I take my thumb in the direction of the current, and then my fingers give me the direction of the magnetic field. It's clear that the magnetic field is going to thread its way through this system, the solenoid, like that. So the north pole of the solenoid would be this one, and the south pole of the solenoid would be that, because north is where the fields emanate from and south is where they get sucked into. And the same thing here, I don't have to repeat. The current direction is all that matters for the magnetic field. Like that. So this is the magnetic field B. So as far as coils go, they produce a magnetic field when current is flowing through them, and there's nothing more to be said. Outside the field is zero, and inside it's there. It's called mu naught Ni. That's the magnetic field of a solenoid, and that's all you knew before. But what if current changed with time? Now the little I gives you an indication that current is changing with time, because that's my notation. Let's suppose particularly that the rate of change of current is bigger than zero in this case. That means this magnetic field B is getting bigger and bigger. Well, by Faraday's law, the coil does not like this state of affairs, because the flux going through any cross-section of the coil, if you think of that as the Faraday loop, is increasing. It's increasing in this direction. So the coil wants to do the other thing. It wants to put a magnetic field out in this direction. So for that purpose, the coil would have to put an induced current in this direction, in the opposite direction. Now that Henry, who was a US physicist working in Princeton, Joseph Henry, they even have a lab named after him, Joseph Henry Labs, Princeton, very famous lab, with all his original equipment still preserved behind a glass showcase. So you have induced current in this direction. Now Joseph Henry thought, well, that can be thought of as having a source of EMF. You can think of it as an induced EMF E prime, which is an actual battery that you can imagine to be added to the circuit to produce the induced current I prime that's needed to counteract this rate of change di by dt that's bigger than zero. So he also invented the concept of a EMF direction. So he said, to oppose this change, we have to have an EMF in this direction. What he really means, what the direction of the EMF really means, is that you should imagine having a battery with a large side on the left and a small side on the right. So that's positive and that's negative. So that's really what's meant in modern terms. So the direction of the EMF is the direction in which induced current would have to be put in order to counteract this rate of change of current. Let's try the other case. What if di by dt were less than zero? Well, in that case, any cross-section of the coil will be seeing less magnetic field going to the right, and to remedy that situation, the coil would like to send more induced current such that more of this kind of field is produced, or flux is produced, and that would require an induced EMF in this direction, to use Henry's language. And what that would correspond to in modern circuit theory terms would be having a battery that aligns itself like that in the circuit, producing an induced current E prime, with this being the plus and that being the minus. So these were the observations of Henry, and he called this EMF E prime the back EMF. It makes sense. It is acting backwards in the direction of the increasing trend. If current increases in this direction, the magnetic field increases in the forward direction, and so the EMF kicks back to counteract it. So he called that the back EMF. And he defined a quantity called the self-inductance of the coil. And the self-inductance, sometimes simply called inductance without the word self, is the back EMF that's generated by the coil in response to the change in current per unit current rate. So this is like a advanced Ohm's law. So L is a symbol for self-inductance, and you put a minus sign there. I'll explain that in a second. E prime over di by dt. That minus sign is just Lenz's law in action again. So that's Lenz's law showing up this time in Joseph Henry's law. Now the units are very important. The units of inductance in honor of Joseph Henry are called appropriately Henrys. So let's write that. The units of L are Henrys. And let's see what it amounts to. It's volts divided by ampere per second. So the second comes up. So volt second per ampere is equivalent of Henry. Now Faraday, meanwhile, had independently, believe it or not, discovered Faraday's law. So Henry and Faraday were operating on different continents, and back then scientific journals were extremely slow to disseminate themselves. So Faraday's law was well hidden from the world, and Henry's investigations were likewise well hidden. So Faraday's law, meanwhile, says the following. I'll use the same symbol for the induced EMF. E prime equals negative rate of change of magnetic flux through the coil. Now I'm going to set these two expressions for E prime equal. So here I have an expression for E prime, which I'm going to write as E prime equals negative L di by dt. By the way, written in this form, this is called Henry's law. That's the definition of self-inductance, but written in this form, it's called Henry's law. And it's as important a law as Ohm's law. Ohm's law says V equals IR. This one says E equals almost like voltage equals something like resistance, but it's called inductance. But instead of current, we have the rate of change of current. So take Henry's law and Faraday's law together and set them equal. Well, that's the natural thing to do because the left-hand sides are the same. So if you do that, you get negative L di by dt. So what I'm doing is I'm putting E prime on Faraday's side equals E prime on Henry's side. And that's equal to negative d phi b by dt. The negative signs can cancel out, and then you can also integrate both sides. When you integrate both sides, L comes out of the integral sign, and the dt's kind of cancel out. This is all very hokey calculus, but you can do this very rigorously. So L delta I becomes delta phi. And that's the first fundamental theorem of calculus. The integral of a differential is same as the change. So that gives you a nice way to actually measure the self-inductance of any coil. What you do is you send some current through it. Now what's usually done is initially you don't put any current through the coil. So the initial, this delta, capital delta means final minus initial. So initial, if you take the current to be zero initially, the flux is also zero. So this just turns out to be flux, the new flux divided by the new current. So that's a great way to measure the inductance of any coil. Now coils can be very complicated. You can have a coil that suddenly increases in the number of turns or suddenly changes its cross-sectional area. So working all those things out using calculus is a nightmare. So you can actually do this experimentally and get the self-inductance very nicely. Now there's one important object whose self-inductance is sacred, almost as sacred as a parallel plate capacitor. So this is the parallel plate capacitor analog of inductor theory, and that is a solenoid's self-inductance. So let's focus on that. And when I close this video, I'll talk a little bit about mutual inductance, but not too much. It's sort of a peripheral aspect of this course. So let's derive an expression for the solenoid self-inductance. When you work with inductance long enough, you'll realize it's actually a geometric thing. And a very great scientist called Gauss realized it, and many of his famous theorems, which are staples in the mathematical subject of knot theory, come from his early investigations of inductor theory. So let's go back to the solenoid. Let's put some terms here. That solenoid that you have up there, let's say that it's got n turns per meter, or turns per unit length if you don't want to commit to a unit system. And let's call capital N the total number of turns. So the total number of turns is going to be the turns per meter times the length of the solenoid, and that'll give me the total number of turns. So I'll just put the length of the solenoid here. I'm always amazed by you take a piece of wire, it's nothing, and then you just wrap it around a pencil, suddenly it becomes an energy storage device that stores magnetic energy. It's one of the most amazing facts of life. The cross-sectional area, which I've shaded here for other reasons, can be called capital A. So now I'm ready to find the self-inductance using this basic definition. I'm going to assume that initially there's no current, so all I have to do is find the flux right now and divide it by the total current. Well, the flux right now is a flux through the solenoid, through the open surface. It's got n turns, and then the definition of flux is B dot dA integral and all that, but for this case it's just B times the area, and then you have to worry about the dot product. I'll just say it's cosine 0 degrees because I'm not interested in producing a negative sign with inductance. So I have everything here. The solenoid's magnetic field is well known. It is mu naught Ni, little ni, and times the area A. So I've done, the only problem here is I have two kinds of n's, capital N and little n. Let me eliminate little n. Little n is capital N divided by L. So I get mu naught times n squared A I over L. That's the flux. And the inductance is just the flux per unit current. You should think of this as how we found the expressions for capacitors. We found everything in terms of charge, and then we divided out by charge to find the capacitance. In the same way, we're now dividing out by current to find the self-inductance. So this is going to be mu naught n squared A over L. Really interesting expression. So this should be thought of in the same spirit. So I don't know how to indicate spiritual equivalence. So let me just write spirit. And the spiritual equivalent of this is the parallel plate capacitor formula. C equals epsilon naught. There's no number of turns there, so it's just going to be area over the distance separating the plates. You notice the similarity, the kinship here. There's constant of nature. Here it's mu naught, there it's epsilon naught. There's the area, and then there's the distance. So epsilon naught, by the way, had interesting units. Capacitance is measured in farads. So this is farads equals epsilon naught, units of epsilon naught times meter squared over meters, which is just meters. And so we now know epsilon naught value to be something like 9 picofarads per meter. And we're going to have similar cool units for Henry shortly. L is measured in Henry, and mu naught, well, we need to find the units of mu naught. Number of turns has no units. Area is just like that, meter squared over meters, so it's mu naught times meters. And now we have units for mu naught. So let's write out what mu naught is. Mu naught is 4 pi times 10 to the minus 7. Previously it used to be tesla meter per ampere, now it's Henry per meter, just like that. And to make it look even nicer, 4 pi is about 3.14, is it not? So that times 4 is something like 13 approximately. So 13 times 10 to the minus 7 is 1.3 microhenry per meter. So this is how workers in the field rationalize the capacitance or the inductance of any object. So if I have this object, it's a complicated looking thing, it's made of metal, I can roughly give you the inductance by saying, how big is it? It's about 1/10 of a meter. So it's 0.13 microhenry. And that's it. It doesn't mean anything. I mean, because you have to still specify with respect to what the inductance is, but it gives you a ballpark value of inductance. Just like I can say the capacitance of even a wooden object like this is something like 9 picofarads per meter, and that's 1/10 of a meter, so it's 0.9 picofarads. Now I'll leave it for the person to struggle to understand what that means, but it's got a length, it's got a capacitance, it's got a length, it's got an inductance. So that's the self-inductance of a solenoid, a very important expression. Now there's something called a mutual inductance, and I've developed this in the notes in some detail, but I just want to talk about this for a couple minutes here. The mutual inductance concept arose from the experiments of Faraday, where he had two coils, and this I show in the demonstration video of the previous week. You have two coils, you do something to this coil, and a deflection galvanometer attached to that coil shows a deflection. Now to rationalize that, Faraday, actually Henry also, thought about finding a way for these two coils to talk. And it's in the context of these two coils, the two coil problem, that some of Gauss's greatest work in topology was done, and not theory. So this is coil A and that's coil B. How does rate of change of current in coil A affect the flux through coil B was the big problem. And then to address this problem, the concept of mutual inductance was invented. So what we're going to define here in the last line is the EMF through coil B is defined as negative the mutual inductance of B with respect to A, the rate of change of current in coil A over time. So you can imagine that there's a flux through this coil. I'll call this phi B A, and there's a flux through this coil, and apologize for the notational confusion. So it's phi B B, where the second subscript refers to the coil and the first subscript refers to the magnetic field. And that's the definition of mutual inductance, MBA. And the mutual inductance MAB is defined as follows. And this completely gives you a crosstalk between those two coils. It was the great Gauss who proved the mathematical theorem that MAB equals MBA. One of the most famous results in topology or not theory. So once you have Gauss's theorem, you can actually use it to great advantage, because in many electrical problems, one of the inductance is trivial to find and the other one is incredibly hard to find, but thanks to Gauss's theorem, you can find the easier one first.